F prime provides us with a lot of useful information about a function, but it's not enough to get an accurate picture. What we need is something more beyond F prime. Now, as an example, here are two pictures of some functions, and in both cases, you can see that no matter where I draw a tangent line, the slope of the tangent line will be positive, and in both senses, F prime will be positive everywhere. So as far as F prime is concerned, these two functions are kind of the same. They're both positive derivatives, but our eyes can see that they are clearly not. We need to talk a little bit more about what is going on here. We can see that here we have very steep slope, whereas here we have a shallow slope. Now, the other way, or the other picture has the opposite. We have very shallow slopes and we have very steep slopes. So yes, both of them have positive derivatives, but what's happening here is that the F prime value is decreasing because the slopes are getting more shallow, whereas over here, the F prime value is increasing. Now, if we connect what we did before, remember that when a function, any function, even if it's F prime, when a function is decreasing, that means the derivative of that function has to be negative, or F double prime is negative. Now, when a function, any function, is increasing, that means the derivative of that function has to be positive. Well, we know the derivative of a derivative is the second derivative. So what we've got here, just from a simple observation, is that the second derivative tells us something more. So the next piece of information is that we talk about something called concavity. And this is how you could think of very simply how the graph bends. And it's related to F double prime. Now you could prove this or the result that we talk about could be proven in a sec. So I'm just going to label those or draw those pictures again. And I'm going to talk about what I'll jokingly call the different flavors of concavity. In this first picture, we had the derivative was positive, but the second derivative was negative. Whereas in the second picture, we had the derivative, the first derivative was positive, but the second derivative was also positive. This case, I'm going to call second derivative negative. I'm going to call this concave down. And the reason I'm going to call this concave down is that you could imagine that the graph is like a smiling face, and the graph opens downward. The tangent lines are always above, and maybe a better way to say it would be relative to the title. The function is always below its tangent lines. So no matter where you draw a slope, the tangent lines will be above or the function is down. It's down below the tangents. And one way of thinking about it that was told to me when I took calculus was that this doesn't hold water. So if you were to put a little drop of water on a concave down function, it would just roll off. It couldn't stay put. Now, if you've got a situation like this, we are going to call it concave up. The graph of the function smiles. It opens upward. The function no matter where you draw a tangent, the function is above or up above the tangents. And you could think of the graph as being able to hold water. It's like the bottom of a bowl. You could imagine that if I were to put a little drop of water, it would stay put in the bottom here. So those are all different ways of visualizing or developing some intuition about what it means to have a function that's concave down and concave up. Now, in terms of mathematics, we can prove, and again, we would use the mean value theorem and some tangents, the idea of the tangents to this function, that if the second derivative is negative, that means that the function, the original function, is concave down, or I'll just call it CD. And if the function has a positive second derivative, we will say that the function is concave up, CU. We are going to be interested in finding the concavity of my function. So that means I have to take the function, find its derivative, then find its second derivative. And then I'm going to build a sine table for it. Because what I'm going to do is examine the signs of the second derivative and come up with the same idea. Wherever the second derivative is positive, my function will be concave up. Wherever my second derivative is negative, my function will be concave down. So I'm going to find the regions of concavity. Now there's a special kind of point. For the first derivative, we have these special points called critical numbers. There's something similar for a second derivative, but you have to be very careful. The definition is subtle. It's called an inflection point. So it's a point on the graph of a function that is continuous where f double prime changes sign. So remember how the first derivative test was all about where the first derivative changed sign? We are going to be interested in hunting for spots where the second derivative changes sign. This is not called the second derivative test. There's something else that's going to be used for that, and we don't use that. So the terminology is a little bit funny. I wouldn't get into that right now. The process that we're going to talk about here is the following. So I'm going to go back to that example that I mentioned earlier and say, look, the function here is x squared over x squared plus 3. It's continuous everywhere. So there's nothing funny to worry about. I stated, and you should be able to verify this pretty easily, that the derivative is this. And now you should also be able to verify very easily that the second derivative looks like this. Now, there's a lot of work to get to that, and I would recommend that you pause the video and figure out how to get to this result. Now, we found that f prime was 0 at x equals 0. From here, you should be able to factor this second derivative even further. So, f double prime will equal 0 at x equals -1 and +1. F double prime always exists. The denominator will never be 0, so you never have to worry about it being undefined. So we are also going to build a sine table for f double prime. So we put those special, I guess you could call them critical numbers for f double prime. and then we split up the number line, and then we put the factors of the second derivative here. So we'll have a negative 18, x plus 1, x minus 1, x squared plus 3, all cubed. It's really, really important that you factor everything. Your life will be much better off, and I've been trying to convince some of you along the way to do this. Once you've got the factors, determine their sign in each one of these regions. Negative 18 is always negative. X squared plus 3 is always positive. It doesn't matter if you cube the whole mess afterward. X plus 1 changes its sign only once, and that happens across negative 1. So when I'm less than negative 1, like negative 10 billion, that's positive. But when I'm greater than negative 1, say at 0, when x is 0, that's positive, and the bigger I get, the more positive it gets. There's a similar thing that happens here for x minus 1. It only has one sign change. It's at positive 1. When I'm less than positive 1, so let's say negative a million or 0, both of these factors are negative, but it only switches its sign there. So I put it all together. These four factors multiply to give me the overall sign of f double prime. So I multiply their signs. Negative, 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 positive. This gives me a negative. Two negatives give me a positive. And this is a negative. So what does this tell me? This means that the function here is concave down from negative infinity to negative 1, round brackets. Concave up from negative 1 to positive 1, round brackets. And concave down from 1 to infinity. Because I have a sign change of f double prime, that means that x equals negative 1 is what I call an IP, inflection point. And because I have a sign change, x equals positive 1 is also an inflection point. Inflection points are points where the concavity changes. It switches from concave up to down and vice versa. And once you've got the first derivative information, once you've got the second derivative information, you can put it all together. Now, the one last thing, again, that I'll mention, an inflection point needs to have a continuous function. If you have functions where you are not continuous at that point, not an inflection point. So even if you have something like this, where you're concave up and concave down, and if you have a dot there, that doesn't count, because that point is not continuous. So what we are going to do is take the results of everything that we did today and put it together. So we're going to combine all the info about f, f prime, and f double prime. And we're going to use this to draw a graph of the original function. The way I like doing this is by drawing sort of a number line, and I'll switch pages here. I don't necessarily know everything about my function, but when I look at the definition of the function, it was always positive. It's x squared over x squared plus 3. Next week, we're going to get into all the information that we need to gather in order to get a good picture. But for now, if we talk about f prime, remember that f prime was decreasing until I got to 0, and then it was increasing afterward. So it goes down, and then it goes up. F double prime was concave down until I got to positive 1. It was concave up from negative 1 to positive 1. And then it was concave down. So I'm just going to walk from left to right and try to sketch in the graph of a function that behaves this way. So for example, if I start over here somewhere, my function has to continue, has to drop, has to decrease, and be concave down. So it has to kind of do something like this, dropping and frowning. As soon as I cross, I still have to be decreasing, but then I have to be smiling. So there's an inflection point right there. I'm dropping but smiling. So I'm frowning there and I'm smiling here. Afterward, I have to be increasing and smiling. So I have to be going up again. So facing up. There's another inflection point right there. And I will then continue to rise but frown. And so you can see that a lot of good information is given to us. Things that we don't know are, okay, what's the height? What behavior do we have here? So the last little bits of the puzzle are going to be, let's study what happens really far out. So we're going to revisit end behavior, and then we're going to come up with a process to put it all together to get very accurate graphs of functions.